This is a proximity graph. The connections between the nodes get brighter the closer one node is to another. If we take the brightness of the connections to represent a force between the nodes, this is what happens. This is a proximity graph with gravity. And this is what it looks like if we reverse gravity. It's actually not that hard to build this, and in this video I'm going to show you how. So how do we build this proximity graph? Well, a lot of the code we need is actually already in the previous video on how to build Pong from scratch. If you haven't seen that video, I'll put a link up in the top right corner, but it's not mandatory. What I'm doing right now is just going through and removing some of the code that's really specific to Pong, like everything that had to do with paddles and players and scoring points. If you don't want to go through all that, I'm going to give you a link to some code you can use as a starting point. And what we're going to do is add back in the reflection off of the right and left walls here. So we're just going to copy this over, change this to X, and copy this. And put it down here. And now we're just left with the ball bouncing around. This ball is going to be one of our nodes. But first, I'm going to modify some of the canvas setup code just to make things a little bit nicer. What I'm going to do is I'm going to scale the canvas to be the width of the document here so that it expands the entire usable area of the screen. The way we can do that is just say document.body.outer offset width. So now it'll expand all the way, and I'm going to set the height to be the same as the width. So whatever this screen ends up loading into, the canvas is going to resize in order to fit into that screen area. The second thing I'm going to do is I'm going to actually zoom out the canvas and rescale it so that we can have a higher number of pixels per inch. And this is going to make it look a little bit better on a Retina screen. And I'm actually going to do it in a way that actually scales everything down and zooms out. Instead of keeping everything constant. So all I'm going to do is just add a little zoom factor, and I'm just going to set it to 2 for now. And I'm going to multiply that into the width. So now the width of the canvas is doubled, and what we need to do now is scale everything down. And the way to do that is to just say canvas.style.transform equals scale, and I'm actually going to use a template string for this. So right next to the 1 key is a little what almost looks like an apostrophe, but it's not quite an apostrophe. It's a backtick, and this allows us to create a string and put variables inside the string really easily. So I can say scale, and I'm going to rescale it to 1 over the zoom, which should be a half. So if I do $ curly brackets and 1 over zoom, now it's scaled the canvas down. And if I set style.transform origin to top left, it'll align nicely. Okay, so now what we want to do is create a bunch of circles that are all bouncing around inside this simulation. But when we wrote this for Pong, we only had a single ball, and So that's not going to work as it is. We're going to need to modify all of these edge bounce conditions and the movement so that it works with more than one ball. And the way to do that is we can create an array. And that's basically a list. And we can say, we can loop through this list and move every single one of those objects, every single frame. So I'm just going to call this array nodes, and it's going to be empty for now. And I'm actually going to put this all the way up at the top. That's going to live throughout our entire program. And now what we need to do is create a function that creates a bunch of nodes and adds them to this array. So we should go down and create a setup function that's going to do all of this initialization and set up all of these objects. So we have a setup function, and we're going to create a for loop from 0 to some number for the number of nodes that we want to create. And every time it loops through, we're going to create a node and then add it to the nodes array. So we can say nodes.push node. So next thing we need to do is create this create node function, this factory function. And so we can go up here and use our ball code, create node, and it should return this object. Return node. And we can delete this. So it's still not showing up. All of these nodes still aren't showing up. And they aren't going to until we fix all of this code that references the ball. Instead of the ball, this should be run for every single node. There's actually an easy way to do this. And what I want to do is say, instead of moving a circle, I want to have a function that moves the nodes. And I also want to have a function check edge bounce that will check the edge bounce of every single node. So in our move nodes function, we should have something that iterates through that list of nodes and moves every single one of them. So if we create a new function called move nodes, and we should have a for loop that goes through all of the nodes. There's a more modern way to do this in JavaScript. We can say for node of nodes. And let's imagine that we have a function on this node object that just moves the nodes. We should probably provide it with our dt parameter, our time step, dt, and I should go down here and specify dt. And we're going to have to create that on our object, that method. There's a nice way of doing this. We can say move bracket dt, and this specifies a method on this object. This method should just use our physics equation from the Pong video. So I can copy that, put it in here, and instead of ball, it should be the node. So let's just change that to be node. That should be good as it is. We can delete this old move circle code because we don't need it anymore. And let's comment out this edge bounce and see what happens. So it's still not working, and that's because we need to actually draw each of these nodes too. So if we want to draw this, we should probably have a loop as we do in the move nodes, and this loop should draw every node. So we can do the same sort of strategy and say node.draw, and imagine we have a method that draws the node. We can copy this old draw circle code, go up into the create node function, and add a method called draw. And change the ball to node. All right, so it looks like we have one ball, but actually we have 100. They're just all stacked on top of each other. So we should probably do some changing of the initial position of each of these nodes. Let's just do something a bit naive for now. Let's just say node.position.set, and we can set it to a random position. Let's say math.random times width and math.random times height. There we go. They're all moving in the same direction like a flock of geese. Actually, I don't even know if geese move that way. They probably don't. We should probably change the velocity. Node.velocity. We can just use our randomize method. There we go. Not bad. So the only thing left to do is our check edge bounce. We should have this run for every single node as well. So how about we do the same sort of strategy, and we copy a for loop, put it in here, and we can call a method called check bounce. Let's call it check edge bounce for each of the nodes. Copy this old code, create a method, check edge bounce, paste it in here, get proper indentation, and we can Control D or Apple D to get all of these references to ball and change them to node. And it looks like it is not working. Oh, that's because we commented this out. So let's comment this back in. There we go. Particles in a box. So looks like some of them are struggling a little bit down on the edges. That's probably because of our random conditions. They got stuck inside. What we can actually do is make this edge bounce a little bit nicer and more robust. If the node position is just outside of our box, we can shove it back into the box just at the boundary. So we can say that node.position.y should equal the height minus the node radius, and do the same thing for the rest of these conditions. And there we go. That looks way better. So now we can start having a little bit of fun here. I'm going to change the color of these nodes. I'm going to make them a crimson red. And I'm going to set them to be much smaller. That's a radius of 6. And that looks, let's make them a little bit bigger. Okay, that's a radius of 8. That looks okay. They're going a little bit fast, so how about we change this randomize? And I'm going to randomize this in a little bit of a different way, and I'm going to introduce you to what I think is one of the most useful functions that I've ever come across in programming. I use it for so many things. It's called lerp, and it stands for linear interpolation. So I'll explain what that means. Lerp. So this lerp function effectively takes a minimum number, a maximum number, and some value. And what it does is, if you specify a value of 0, it's going to take on this minimum value. It's going to return min. If you give this value of v equal to 1, it will return the maximum value here. And if v takes on any amount in between 0 and 1, it will scale it between min and max proportionally to that value you specified. So let's get an example here. If I use this function and I said lerp 3, 5, and 1, then the value it returned would be 5, because this last value is 1. If I set a value of 0 here, it would return 3. And if I had a value, for example, of 0.5, it would return 4, because 4 is halfway in between 3 and 5. So this ends up being really useful. And the way to make this function is actually really simple, and probably worth committing to memory if you're thinking of using this in future. If you're going to be coding a lot, it's worth just committing this to memory. And all we need to do is say max minus min times v plus min. And that should be our lerp function. So how are we going to use this for the initial conditions? Well, for our position, I'm going to use the randomize function, the randomize method on our, ooh, that's really neat. All sorts of happy accidents happen when you start coding and don't pay too much attention to what you've written. I love that. That's really neat. Anyways, what I'm going to do is use this randomize function method on our position vector, and I'm going to set it to be some value, some random value in between 0 and the half width of our canvas. So the way I can do that is say lerp anything between 0 and half of the width of the canvas, and supply a random number between 0 and 1. So this isn't going to do exactly what I want until I shift the position into the middle. So I need to shift this position by half the width and half the height. It'll probably come in handy to have a reference to the middle of this canvas in future. So I'm just going to create a little vector at the top here called middle, and set it to be half the width and half the height. And that's going to be a vector that just points to the center of the canvas. So if I add that to our position vector, it starts things off really quite evenly. There are actually going to be a little bit more in the center, a few more nodes in the center of the screen. And I kind of want that because it gives a nice effect. But this is mostly going to be even in all directions. So we can do something else for our velocity. I want a velocity between, let's say, 0.05 and 0.1. So lerp, I want it between 0.05 and 0.1. And give me a random value in between 0 and 1. And that should scale everything nicely. Those look a little too slow. Let's just speed it up a very little bit. That looks good. Maybe 0.2. That looks okay. Got some nice variation in between there. And they're bouncing around. Just for kicks, I'm going to darken the background of the canvas. And you might remember that's in style. We can delete all this scoreboard code, actually. We don't need that anymore. And I'm just going to darken this to, let's say, there. That looks pretty good. So what we need to do now is create connections in between all of these nodes. So let's just draw some lines between every single one of these nodes and see what happens. So every single frame, we should draw lines from every single one of these nodes to every other node. And we're going to do it before we draw the nodes so that any lines that get drawn don't overlap the nodes, the circles themselves. So whatever we draw last is what ends up on top. So I'm going to call a function that doesn't exist, draw connections. So draw connections. We could set up a for loop, for example, like this. We could say for node 1 of nodes, for node 2 of nodes, and then do something in between here. But if we did that, we would double up all of the connections. So it's a little bit inefficient to do it this way, and we're going to end up double drawing all of the lines. So there's something better that we should do, and we should actually use a good old-fashioned for loop for this with numbers and iterate through the indexes of the array. So we can say let I equal 0. I is less than nodes.length, I plus plus, and our second for loop, we can use j as a counter, and we don't want to start at 0 again because that's just going to draw every node to itself. We don't need to do that. So we can start at whatever the value of I is plus 1. And again, j should be less than nodes.length, and we should have j plus plus. Let's clean this up a bit and pull the length out here. length, and length. And now we can say that we have node 1 is nodes I, and node 2 is nodes j. So now we have a pair of nodes that are always going to be different nodes, and we can say we want to draw connection between node 1 and node 2. So let's make that function. Draw connection node 1, node 2. What we can actually do is use the debug draw on the vector library to draw the vectors, the displacement vectors in between each of these nodes. So to get the displacement between two nodes, we can say node 2.position dot minus node 1.position. Let's say that is displacement. And let's do a debug draw. Displacement.debug draw. Pass it in the canvas context. So now it looks kind of strange, and that's because we need to draw these vectors from the node 1 position. All right, so our processor is kind of overloading right now because there are so many connections. I'm going to comment that back out. We can't draw all of these connections every single frame. And it also just looks way too messy. So we should have a maximum distance that two nodes can be away from each other, so that if they're within that maximum distance, we draw the connection. And if they're outside that maximum distance, we just don't do anything. So let's set a constant called max distance. And let's set it to be 200 for now. Actually, make it 300. So if this displacement has a magnitude greater than 300, we should just not draw this. So we should say if displacement dot norm is greater than or equal to max distance, then return. Just a little note, some people might, instead of doing this, they might say if displacement norm is less than max distance, then draw. But then you end up with code, a lot of code inside of the if statement. And I find it a little bit cleaner to just return from the function early instead. That way we can just have our draw code right below, and it does exactly the same thing, but we don't end up with nested if statements. So it's just a little thing to keep our code a little bit cleaner and easier to read. So now let's draw this displacement. There we go. That's looking a little bit better. Let's maybe reduce this to around 200. That looks okay. So already we have a proximity graph here being drawn. And from here, we can do a lot of fun things. something kind of neat is if we add some other parameters in here, like maybe I could scale the vectors by 2. This looks kind of neat. Or if I want to draw the components of every vector here, I could say true. And then we end up with some super wacky visualization here. I really love just playing around with the code and seeing what happens. Sometimes you get really neat results like this. But we could also change the color of these connections. And let's set a color variable. And let's just set it to steel blue for now and put that in here. But ultimately what we want to do is we want to make these connections dimmer and dimmer the farther they are away. So if they are right at the maximum distance, they should basically, the connection should basically be transparent. And if they're closer, we're going to increase the transparency of this color. So in order to make this color scaling, we should use the HSLA color space. And this stands for hue, saturation, lightness, and alpha. Alpha being the opacity. The hue is just the value on a color wheel, so it's a value between 0 and 360 degrees. I actually have a color in mind. I'm going to go with 180, 90%, 60% for this nice light blue color. And we'll just start with an alpha of 1. So our saturation is at around 90% and 60% lightness. You can play around with these values as much as you like. What I want to do, though, is scale this opacity, this alpha value, between 0 and 1, depending on the distance that the nodes are away from each other. The way to do that is to use another extremely useful function called, I'm going to call it rescale. And it's also called min-max normalization. And basically what this function rescale is going to do is, we'll pretend that I have it here, is we can give it some minimum value, let's say 20, and a maximum value, let's say 100. And whatever value we put inside of here it's going to be a value between 20 and 100, and it's going to return a value between 0 and 1. So it's almost like the opposite of a lerp. Instead of returning a number between the minimum and maximum, it takes in a number between the minimum and maximum and returns a number between 0 and 1. So in order to create this function, I'm going to call it rescale, and it's going to take in a min, a max, and a value. And all we need to do is return value minus min divided by max minus min. So that's our rescale function. And we can use that to change the opacity value on this color depending on the distance the nodes are away from each other. So the distance is displacement norm. So we might as well just put that inside of a variable, call it distance, and that's displacement norm. And we can get the alpha by saying rescale 0 max distance and pass it in the actual distance of the nodes. So now we have this alpha value, and again we're going to use that backtick in order to put this variable inside of this string. So $, curly brackets, and alpha. And that is not working how I want it to, because this is actually the opposite of what I want. I want a number between max distance and 0. There we go. That's looking much better. It looks like tiny little spider webs being created and destroyed in between these nodes. So we can actually just play around with this max distance if we want to get a little bit more density in the lines. We can get a slightly better effect if we also have a minimum distance. So instead of having a 0 here, where the color, the alpha, gets to its maximum value, which would basically be the nodes totally on top of each other, which means we can't really see the line anyway, we should have a minimum distance where it gets to that maximum color, that maximum alpha value. So let's create a min distance, and we can set it to say 50, and put min distance in here. And that's going to be a little bit of a nicer effect. You can also play around with this. Maybe 100 looks better to you. I think I'm going to keep it at around 50. I sort of like that. So it might be a little bit laggy for you, depending on the power of your computer and how many points, how many nodes you have. There's some things we can do to optimize this. First of all, using the debug draw and drawing the actual vectors, the displacement vectors, is not very efficient. We should make a better line draw function. But also, a huge optimization we should do is actually down in the animation loop. So what we've been doing so far is using a set timeout to call the animate function over and over again at a short delay. But what web developers actually do that is a way better method is to use a function called requestAnimationFrame. And what that function does is almost the same thing as set timeout, except that it hands off the frame rate to the computer so that the computer can make a decision about what the frame rate should be. And it allows the computer to make some optimizations there. The downside is that we don't have a constant DT anymore. So DT is actually going to change every single frame. But that's no problem because we can just pass in that DT value into the functions instead of having it as a constant variable at the top. So that's no problem. But we're going to have to actually calculate what the DT is. So let's get rid of every reference to this global DT. I'll just delete this global DT and the code is not going to work anymore. And that's because we're not passing it in. So for now, let's put a DT inside here and make sure that our wires are connected before we start modifying everything. We have a frame function and we should pass the DT in there. And that looks like all we needed to do. So this looks fine to implement requestAnimationFrame. Our DT we should change it to a variable, and it's going to be calculated every single frame. What we need to do is keep track of the previous time that the animate function was run. So let's do previous time. We'll start it off at 0. We are going to get the current time. We'll just call it now. And the way we get that in a really precise way is to call performance.now. And dt is going to be the time difference between now and the previous time. So now minus previous time. And then we need to remember the previous time and set it to now. All right. And next, we use requestAnimationFrame. And we can remove this dt here. So hopefully for you, it's looking a lot smoother now just by doing this little change. The next thing we can do is create that line draw function to make it a little bit faster. So instead of using our debug draw in draw connection, we should have our own function that draws a line between 2 points. So we can say, let's comment this out. Let's imagine we have a function called drawLine, and we're going to draw it from node 2.position to node 1.position and give it a color. So we have a drawLine function that takes in a vector and another vector and a color. So vector 1, vector 2, let's call them point 1, point 2, and color. We want to set the color on the canvas, and this isn't going to be fill color or fill style anymore. It's going to be stroke style. And now we want to do ctx begin path, ctx dot, we're going to move to the coordinates of the first point. So p1.x, p1.y, and then we're going to say line to the second point. And finally, we say ctx.stroke. There we go. We should also set a line width, and you can set this to whatever you want. 2 looks pretty good. 1 is a little bit thin. I'll just keep it at 2. And that should be a lot faster than using our debug draw, even though the debug draw is kind of cool because it has those other options for playing around. So hopefully this is running a little bit smoother for you. Now we can really have some fun. We can actually start adding some physics to this. And what we want to do is add a force between the nodes that are connected, depending on how far apart they are. So how do you add a force in a physics simulation like this? Well, we can simplify things and just assume that all of these nodes have the same mass. And what that means is that the acceleration between the nodes is basically the same thing as the force. And an acceleration between two nodes is just a shift in their velocities, a change in their velocities. So if every frame we change their velocities by a small amount, we're going to end up accelerating them in some way. So let's go into the draw connection function. And we're going to do something a little bit hacky here. Normally, if I wanted to write this really cleanly, I wouldn't put anything inside of the draw connection function except for the code that actually draws the connection. But it's already here. All of the distance calculations are here. So we can just use this for now to get an idea of what's going on. So let's do something really simple first. What we are going to do is make a slight shift in the velocities of the nodes along the direction of the displacement vector. And we're going to make it, first of all, by just a constant amount. So let's set up a variable, and I'm going to call it nudge. We're nudging the nodes ever so slightly. And what we want to do is put this nudge along the displacement vector. The easiest way to do that is to take the displacement vector and normalize it first. What this does is it gets rid of any distance information and just contains the information about what direction it is. Once we have that, we can now multiply by some amount, and that can be the magnitude of our nudge. So let's just multiply by some constant. Let's say times 0.3. Let's start with that. Now let's add this nudge to the velocities of node 1 and node 2. So node 2.velocity.add nudge. And I want the other one to be in the opposite direction. So I'm going to do node 1.velocity.subtract nudge. So now this is going a little bit crazy, and that just means our nudge is a little bit too big. So let's just keep adding zeros until this starts to look a little bit better. Okay, so that's a little bit too much. Let's start subtracting zeros until it looks like something's happening. Okay. There we go. So this is a repulsive force at the moment. This positive value is creating a repulsion between the nodes. If we put a negative value here, all of a sudden the nodes are going to pull each other together by a constant amount. So this already is starting to look really cool. If we want, we can increase the strength and get some really weird results here. We can take away the minus sign and they push each other away. So this is pretty cool, but what if we wanted the force to depend on the distance between the nodes? Well, we could just multiply by the distance. And all of a sudden it's too big again, which makes sense because we're multiplying by some large distance. So let's tweak it a little bit. That looks pretty good. I'm just adding and subtracting zeros and playing around with this number. So this force is some constant value times the distance between the nodes along the connection between them, along that displacement vector. And this can also be written as k times x. So k is the constant and x is the distance between them. And this is actually the equation for a spring or an elastic band. The force that we've got here is kind of like an elastic force. So these little nodes, once they get in range of each other and a connection is drawn, they all of a sudden get tied together by an elastic band and then get pulled together. And if we get rid of this minus sign, it's kind of like some kind of a spring between them, and they push each other away. So that is pretty cool. But what if we wanted gravity? you might have dealt with gravity as being a constant force downwards. But that's only true if we're really close to the Earth's surface. Only then is gravity a constant force. Once we get up to the scale of planets and solar systems, we need a different equation for gravity. And that ends up being some constant divided by the squared of the distance between them. So we could write that as x times x, or x squared. And normally we would have the masses in here as well, but we're just assuming that the masses are all the same, so that we could set them to 1 and it wouldn't really change anything. So if this ends up being a negative force, then the gravity is going to be attractive, and if it's positive, it's going to be some kind of anti-gravity and some sort of repulsive force. So let's plug this in and see if we can get some kind of gravitational behavior. So let's do a minus sign first of all, and then we'll do, we need to change this to a divided by distance times distance. Okay. So it looks like nothing is happening, and that probably means that this constant is now too small. And that kind of makes sense because we're dividing by some distance, which is a pretty large number, times itself. So it ends up being a really, really small nudge to the velocities. So let's increase this until we notice something happening. Not yet. No, still needs to be a little bit bigger. Okay, something's happening now. Let's try 10. Okay, so something's happening, and what it looks like is things are getting just flung around like crazy. What's going on here is that the distance can get really, really small when two nodes are almost on top of each other. This distance ends up being really close to 0. And if you divide by something that's really close to 0, it's going to be a huge number. So this nudge in velocity is going to be gigantic. So what we should do is have a little cutoff. And if we're below the minimum distance, we should not apply this nudge. So we can say if distance is less than our min distance, let's just return and not do anything. There, now things are starting to look a little bit nicer. So we've got some orbital behavior here. Let's see if we can increase this. That's looking pretty cool. And if we change this to a positive value, they repel each other like some kind of anti-gravity. And we can play around with these values and tweak it to get it how we like. I'd also encourage you to play around with this equation for the nudge and experiment and see what happens when you change it to different things. Sometimes you can get some really cool effects just by playing around without thinking too much. So in terms of the physics, these were the main things I wanted to show you. And hopefully this gives you enough to play around with. There's so much more that you could do with this. For example, instead of changing the alpha or the transparency of the color of the connections, you could even just change the hue value in roughly the same way. But it would be a value between 0 and 360. And then you get some weird connection colors. They change color depending on how far they are from each other. So I hope you just play around with this and see what happens. And by all means, share your CodePlay links in the comments. I'd love to see what you come up with. You can do that by going up to the project and clicking share and just copy this link into the comment section of YouTube. I'll leave you with a link to the finished product in the video description. in case you want to compare it with your code or play around with the finished product. Hopefully you enjoyed this video and enjoyed playing around with this as much as I do. If you value tutorials like this, you can support my work either on Patreon or on GitHub sponsors, and I'll put links to both of those in the video description below. If you can't support Minute Labs monetarily, you can always share the links and share the labs on social media or with your friends, and that also really helps me out as well. I'm also considering doing a live stream and playing around with these proximity graphs and some of the neat things that you can do with them. If you're interested in seeing something like that, let me know. And if I do decide to do that, I'll be sure to make an announcement so that you all know about it. And until next time, happy coding.